Thank you for the warm welcome. I'm excited to talk about sort of generalization, pre-training, and data-centric views of language models. So the starting point for how I'm thinking about language models, most of my research used to be more on the machine learning robustness side. And so I think about a lot of what's interesting about language models from the generalization perspective. If we stop and think about it for a moment, language models are pretty remarkable in terms of how they generalize, right? Like we can throw at it, all sorts of different tasks, machine translation, entity recognition, so on and so forth, and it'll do great, right? T5, being kind of the precursor of a lot of this happening. If we look at actual, user usage of chatbots, we see similarly a very diverse collection of usages, lots of code synthesis, some stuff that I can't even really talk about in a seminar setting, but we see all sorts of uses of chatbots. I think remarkable that a single system can handle all of this. But I think, we're beginning to realize that there is limits to making things in domain by collecting or using lots of data, right? We've seen lots of work on the question answering and retrieval augmentation settings showing that for niche entities, well, language models don't really contain all the facts, or at least don't reliably answer these questions. A lot of the tests now for language model capabilities are about cutting edge knowledge, right? GPQA being a great example of trying to test for sort of graduate level knowledge and reasoning in the sciences. And then finally, if you're interested, much more on sort of the human-centered side of things like cultures, low resource languages, these are continually going to be problems because there's just not going to be enough internet data for these language models to have good coverage on these topics. So it seems like thinking about data is really important. The other thing I want to sort of highlight is thinking just about pre-training and data similarity. I think a naive view of language models is kind of like what I've put up on this slide over here, right? So pre-training is on these nice high quality websites like Stack Exchange, right? You've got a question and an answer. It's all very nicely written. And then when we deploy these systems, a user comes in and asks something that looks a little bit like a question, and then the model answers it, right? Like very nice match between the two. Kind of the reality of pre-training is that pre-training data is mostly not very good. I taught a class last year on sort of building language models from scratch. And one of the exercises that we did with the students was actually like go and look at your pre-training data. And if you haven't done this before, I think it's very instructive because this is the first example from one of the common crawl dumps that we looked at, right? It's basically blog spam about, I don't know, software tutorials or something. It's completely, I think, low quality by almost any definition of the word, right? And so, pre-training isn't generalization magic. If you train your model on a whole bunch of stuff like this, you're not going to get a very good model back out. And so the performance of modern systems is built on, a team of engineers thinking carefully about what data to use and how to train on these things. So as a person building algorithms, I want to think, can we avoid this kind of handcrafted data selection? Can we have better ways of thinking about data? The second thing I want to talk about is sort of this data efficiency sort of tail domains question. A lot of what language models are good at and have shown success on is kind of the head of the distribution, things where there's a lot of data available. And this nice work on question answering by some folks at UW show this almost very clearly that a language model is even better than a retrieval system answering very popular entities. And then after a certain point, you'd be much better off relying on retrieval augmentation than sort of answering questions directly from the parametric knowledge of a language model. And maybe more broadly, I think data efficiency just seems like a really important challenge broadly. If you're thinking about, enterprise applications and where will these systems be useful, we need to start thinking about how do we best leverage models on proprietary or other kinds of stores, data stores that aren't publicly available. That seems very important. That's on the left side of this slide. If you're a big pre-training shop like OpenAI, then you probably want to think about questions of, okay, there's only a finite amount of internet text available. How can we best leverage that since compute will likely continue to grow, whereas the available stock of text on the internet is not going to grow, or at least high quality data will not continue to grow as quickly, right? And so people have made various projections of varying reliabilities of, when will compute growth outstrip growth of data? Yes?
So I just want to ask a devil's advocate question. Suppose the data doesn't grow, but you just train on it more times. So like you run lots of outliers. will the tail knowledge eventually surface because the gradient's very small on the stuff that's already been learned?
Right. So last year at Murex, one of the best papers was sort of scaling laws for data, repeated data training. And the, soundbite conclusion of that paper is roughly, you have strong diminishing returns, but up to like 5 times or so, you can get, still as if it was fresh data, you get, improvements in the models. The plot on the right actually takes that into account in the sense that the 2027 line is basically the date at which 5x overtraining like roughly starts to exhaust the available data stock. And so this plot already takes that into account. Maybe there's smarter learning algorithms, maybe there's data augmentation. That's kind of going to be that line of thinking is going to be the theme of my talk. Okay. So our approach throughout the 2 parts of this talk is going to be keep things simple and let's try to build on what works. I think there is one line of thinking that can say, okay, let's like rethink the entire sort of training architecture. We'll have a whole new, way of training language models and so on. We're not going to do that. What I'm going to do is to say, can we take what we know works, so language model pre-training, increase scale, all of these pieces, but do it better. And so what we're going to do is to come up with better data selection algorithms and maybe data augmentation methods that will allow us to leverage what already works, but in domains where it currently doesn't work either algorithmically or there's too little data to make it work reliably, right? So that's going to be kind of the general approach that I'm going to take here. So I'm going to talk about 2 different very, very recent works. I'm excited about them, so I put them on this talk. So the first one is going to be about data selection. We know that's in some sense the really core piece that makes language models work. And yet it's so hand engineered. I would like to have some algorithmic sort of hooks into trying to understand and improve data. So that's the very first part, joint work with a first-year student, Tristan, and his co-advisor, Chris. And then I'll talk about sort of domain adaptation and sort of synthetic data style stuff in the second part of this talk. So, okay, I've been emphasizing this before, but maybe this is some light circumstantial evidence as to the importance of thinking very carefully about pre-training data and pre-training data selection. If you look at the Llama 3 report, right, some of our most recent, detailed insights into pre-training, the paper is pretty upfront about what they think is really important to building a high-performance language model, right? Data, scale, and managing complexity, right? Those are the 3 components. It's not maybe necessarily really clever, training architectures and so on. On the data part, they're saying, okay, we need to like really cleverly filter the pre-training data, and they need to get high quality post-training data, things like preferences, instruction following examples, and so on. I'm not going to talk about the post-training part, but it's quite clear from these descriptions that thinking really carefully about pre-training data is really important. And of course, we need to do this at scale, and we need to run these experiments in a way that we can do them efficiently. I'm not going to talk about those either. So now, we know that data is important. So what do people actually do, right? So there have now been several open studies trying to study what kinds of pre-training data is good and works. So let's look at 2 examples. Llama 3.1, I think this is very, in some ways, sad that the state of affairs is, we apply several deduplication methods from a variety of data sources. The details of what they actually do are quite hidden. We don't actually really know what data they use. But it is quite clear what works in some recent open replications of large-scale language model training. I'm going to highlight DataComp-LM as an attempt to do this by some folks at Apple and TRI and academia. They tried to build a high-performance 7 billion parameter model, basically varying all sorts of components in the pre-training data pipeline. And so what do the DataComp people do? Well, the current best-known data selection algorithm is a bigram classifier, and it's very ad hoc in a way. Like, what is it? Well, it's trained to classify random pieces of text on the internet from pieces of text from Reddit's Explain Like I'm 5 subreddit and a instruction tuning data set called Open Hermes, right? Clearly, this is not like the truly most optimal data selector possible, but after a whole bunch of ablations, this is the thing that they found to work. To me, this is quite unsatisfying. Of course, this thing works very well. The performance of the final system is reasonably good, but this is very ad hoc, both in the domains that they've selected and the fact that they're using this bigram classifier. There has to be kind of a better way to select pre-training data. So I want to come up with a principled alternative, an algorithmic data selection procedure with kind of the following type signature. So the inputs are going to be, a target benchmark, a benchmark I want to do well on. I'm also going to take in as input a token count because I can't really do data selection without knowing the total data set size. And then the pool that I can select from, the pre-training corpus. And the output of this algorithm should be some sort of policy for filtering data. It can be, select these domains with some probability, drop these domains with some other probability, so on and so forth. So this is kind of what we're going to try to build towards. We know that there's things that work that are highly hand engineered and heuristic. We would like to at least match them using some very simple algorithmic approaches to data selection. Hopefully, at least the motivation is clear to everyone before I get into any of the selection details. Yes?
That it's a bigram-based classifier as compared to the fact that it's supervised.
I don't mind the fact that it's supervised. In some sense, this type signature is supervised because we have a target benchmark. So, there is some supervision. I kind of think the bigram classifier and the ad hocness of the target go hand in hand, right? It's very easy if you use the BERT classifier. I'm sure you can get like a very, very high classification accuracy on Eli 5 plus Open Hermes, but that's not the point. That's not what you want to pull out. You want to pull out high quality data. And so the bigram is like a blurred out version of that classifier. And so I actually think it's a feature, not a bug, at least for this example. I just kind of think this whole pipeline is deeply unsatisfying from a, what is the actual thing that would really work perspective, rather than building a single artifact. Okay, and we're not the first to think this. I want to just make sure I'm giving the right sort of context for this sub area of research, right? It's really important to understand how data affects models. There's lots of ways that people have thought about this. Two that I'm just going to briefly talk about. There's a line of work that's been recently growing called data models. Basically, this line of thinking is to say, okay, what we're going to do is we're going to take a data-driven approach to understand, training data. We're going to basically have a bunch of different training data sets. We will train different models. And then we will try to go from data mixtures to model performance. We're going to build this big regression model that can go from data to performance, right? And then you can optimize against that regression model. The second class of things that people have done is influence functions, which are in some sense approximations that you can make. You can look at sort of how gradients change when you put in particular training examples, and that can give you some sort of approximation on the behavior of training models with certain kinds of data. And there, of course, there's many other sort of approaches that people have taken. I think the really unfortunate thing is that all of these algorithms make sense. They are quite nice and clean, but they have not changed the data selection process. Large-scale third-party validations of these algorithms have just kind of generally shown that the only thing that continues to work is stuff that's really simple, like bigram classifiers, selection by n-grams. And so I think only maybe DSIR, which is basically selecting based on n-grams, is an algorithmic approach that's ever shown gains at scale. Okay, so why is this the case? Why is sort of, oh, sorry.
It just occurs to me that when you select by n-gram, I started thinking about like not learning rare terms. Maybe you do because they're surrounded by many common terms in a high quality document. But do you only get back English if you're using explain like on time?
So they've already English filtered in their pipeline.
Oh, I see. So that's
which step do they English filter? Yeah, right here. They drop 50.8% of their pool right at the very start because they're only interested in English benchmark performance.
Okay, so if you want a multi-level model, this filter would work.
Exactly.
You need a multi-level.
Yeah, and this I think is part of my complaints about this class of things, which is, these kinds of filters are very ad hoc and designed for specific benchmarks anyway. And so let me step back for a bit and sort of think about why is algorithmic data selection so hard? Well, it's really hard to first principles reason about the behavior of data because, the deep neural networks themselves are very hard to reason about, right? The theory for that hasn't really had the predictive power necessary for us to do something really like top down and principled. And so the only things that seem viable are to basically get some empirical observations, train a bunch of models and see what happens. But each one of those training runs is incredibly expensive, right? I don't want to be training 7 billion parameter models to understand how to select data. And so I'm going to basically train much smaller models, but then your validity gets sacrificed because how valid are those training runs? We don't know. So realistically, this cost validity trade-off really constrains what we can do in this space. And so things that have, been done in the past have sort of been an issue. So let me just concretely walk through this example just to drill this point home. So, my target benchmark is MMLU, right? Standard knowledge intensive question answering. And I want to train a new 7 billion parameter language model on this. So I'm, willing to pay, let's say, like $1 million for this training run. That's roughly, the order of magnitude. Now, if I'm using a data model style approach to do this, one cartoon description of what I would do is I would get 1,000 different training data sets, right? By, let's say, randomly sampling my data. And then I would train 1,000 different models each time with a different data mixture. And then I would say, okay, now I have 1,000 models. I know their training data. I know their benchmark score. I build a big regression model, and then I optimize this regression model, right? I find the mixture that gives me the best performance. Very conceptually simple. Unfortunately, the cost of doing this is I have to train 1,007 billion parameter models. That's basically a non-starter, unless you're maybe OpenAI, but even then you're probably not wanting to actually do this, right? It's not something that you enjoy doing, even with a bunch of compute. So the core idea, the fun trick that powers the rest of this section, or this part of the talk, is that we're not going to train any models, right? In some sense, if you're familiar with say things like causal inference, right, that's the interventional approach, right? We make a bunch of interventions, we see what happens on the other side. Yep.
Could do this experiment.
Mm-hmm.
Is there evidence that the resulting policy or whatever you want to call it would give you a much better model?
Yeah, so that actually, I think the evidence on that is mixed, though slightly positive. The main issue is in this step, when you train 1,000 models, you're training them on a particular data mixture distribution, right? Like, so you have 1,000 training data mixes. Essentially, you can select the best among those, obviously. You can select locally slightly better data distributions, but you can't go very far. The validity of this regression beyond what you trained it on is slightly questionable. And so the results in the literature have been not quite as good, even when people have done this.
What I'm thinking is there even any anecdotal evidence that a different policy than what people are following now could result in a much better model? Maybe something accidental. Somebody just did something, there was a bug. Right. And they suddenly discovered that it's much. Is there any such evidence at all?
Right. I mean,
or is more data just better than data?
Well, I think that at least at that level of granularity, the evidence is quite clear because, some of the older generation language models, they didn't do very much of this filtering at all, or they did some parts of it. And their efficiency of, how much data they needed to get the same performance was truly horrendous. People colloquially say that OPT, which was a model, a couple generations back, the difference between that and Llama was quite a bit of the pre-training data filtering. And so if we're thinking about for a given amount of computational resources, do you get much better models if you do data selection? That answer is quite clear. If it's algorithmic data selection, the evidence there is much more mixed.
For example, a lot of these early things, they're throwing away what, to use the loose term, what is junk.
Yes.
Right. So once I've thrown out the junk, I don't know how much more is left. That was my question.
Yeah, right.
You'll answer it by the end of the talk, so keep going.
Yeah, and I think the other challenging subtlety, which I won't really engage with really deeply, is the bigger model you train, the more data you need. You exhaust the high quality data very quickly. And so now you have to engage with this question of which of the junk am I going to put into my language model, which is a much more subtle question, I think. Okay, so going back to this, the idea is I'm not going to train any models. What I'm going to do is I'm going to leverage all of the publicly available models that exist, right? In some sense, people have trained a lot of models already. There are many, many very high performance models on Hugging Face, over 100 actually, with actually pretty good performance on many things. And so now these models are already trained, so there's no cost. People have attempted to make each of these models good, and for the most part, they're not copying, their data distribution. So it's somewhat heterogeneous. And then finally, there's about 100 models, so we have a decent number of data points. We can't do anything too sophisticated, but this is great because it's a bunch of free data, right? The only issue with all this is that we don't know what data most of these models trained on. Meta doesn't tell us, what their training data set was. So we can't do the naive thing of going from, oh, we trained this data set, we know the performance, we now know what good data looks like, but we do have a lot of models. And that's the starting point for this idea. And the challenge, right, as I said before, is that we don't know the training data, but this turns out to be just fine, right? So what I'm going to do instead, before I was saying, oh, let's build a model that goes from, this is the training data I included, the data mixture, to performance. Instead, I'm going to build a model that goes from log losses, like this is the model's log loss on this domain, to performance. And that's going to turn out to, in some sense, be sufficient to build a data selector. So there's just two steps. So the first step is I'm going to assume that there's this kind of simple looking regression model that predicts performance y of I, right? So y of I is the benchmark performance for model I, and that's a function of theta, which is a fixed parameter. I'm going to estimate that. That's kind of the value of data of each domain, and x of I, which is the log loss that the model attains on domain I, right? So this is an assumption. If this model holds, then we'll get to do some fun things. The step two is now I have to turn this regression into a sampling distribution. And the kind of nice thing is, suppose that I'm able to find a theta star, my regression parameters, that are also non-negative. That turns out to have this very nice property. Notice how I have an inner product between theta star and x. Well, that's linear. And if theta star is non-negative, I can just kind of rewrite that as an expectation, right? So in other words, the one-liner is, if I can find a good non-negative single index model, then sampling according to the weights of that regression, proportionally according to that weights of the regression, is almost by construction a good data selection policy, right? So this is kind of the conceptual basis. I'm going to first build this regression that goes from loss to benchmarks, and then I'm just going to sample proportionally to those regression weights. And of course, the question is, does that kind of work? The details of this algorithm are fairly simple. So I first have to fit the regression. We tried a lot of different ways to fit the regression. I can talk about the various ones. But what turned out to work is, in some sense, amongst the most simplest things you can do. So you just go through each of the different domains, and you estimate what looks like a rank correlation coefficient. This gamma j thing is basically measuring whenever yk, the model yk, is better than the model yl, what is the relative ranks that they attain on the losses, right? So you can think of this as being like a Spearman correlation. It's a rank correlation coefficient that operates on each domain. So the idea here is, if a domain has high rank correlation between the loss and the benchmark, that's probably a high quality domain on the whole. And then to select the pre-training data, gamma j's are not going to be non-negative. So I'm going to do a projection step to project them to be non-negative. And we're also going to do something a little bit different, which is I don't want to sample tokens more than once. And so I'm going to sort of clip the weights at the maximum number of tokens that I have per domain, just to avoid sort of duplicating the data. Finally, the last thing that I'm going to do is this will give us a whole bunch of weights. And I'm just going to train a fastX classifier to classify between things that were selected and not selected. This will allow us to basically select data at a much more fine-grained level than this actual regression coefficient. This allows us to scale a little bit better. I don't want to get into the math here, but the one thing that I thought was very cool about this whole procedure is you can kind of justify this from really classic statistical estimation theory. The estimator that we ended up with on the bottom over here, that turns out to be very closely related to some really classic results in high-dimensional regression by Plan, Verschining, and Udavina, which was extended by Chen and Banerjee in 2017. Like basically, the one-liner here is that they showed various kinds of correlation coefficient estimators are consistent estimators for the regression coefficients of a single index model. So in some sense, the simple thing is also an okay thing to do to estimate single index models under a particular design. So the thing that I'm hiding here is that I'm assuming that the xi's, which in our case is the losses, is independent in Gaussian, which is not a true assumption, but maybe a reasonable approximation in some cases. Okay, so actually I'm gonna skip some of this. What we show is that our estimator, which is a variant of the thing that we showed before, is actually consistent for estimating the parameters of the single index model. But I think in some sense, okay, that was hopefully a nice and clean, and at least top down, all of the steps make sense as a data selector. But the fact that it makes sense doesn't mean that it's going to work, right? I think I emphasized that at the very beginning. Many have tried, and many of the algorithms also haven't worked when we actually train these models. So, okay, how are we going to validate this? We are going to actually build our regression by taking around 90 public models and estimating all of these perplexity correlations. I'm going to target 8 different benchmarks, and I've chosen these particular benchmarks because they're benchmarks that have non-trivial performance, even at really, really small models. We saw that in the Pythia paper, these benchmarks have good readouts even at 70 million parameter models. And we're going to train and evaluate a bunch of tiny models at 160 million scale. This just allows us to iterate sort of very quickly and also get ablations in, which is something that we want to do. And we're going to compare to 3 different baselines, no filtering at all, a reasonable language filtering baseline because we have multilingual benchmarks. And then we're going to compare to the best methods that we know that were validated at the 7 billion parameter scale, which is the FastX classifier and the DSIR n-gram overlap based method. So, okay, how well do these things actually work? What is clear, this is the average rank by method. And so lower is better. Near 0 is where we sort of want to be. And so there's clear separation between sort of 2 classes of methods. The methods that don't really do much better than doing nothing, which is sort of the 5 methods at the bottom here. It's sort of doing no filtering at the very bottom, just language filtering, DSIR here. And then the top 2 here, this is the handcrafted FastX filter. But you actually have to be really careful about this because the original implementation ships with an English language filter, which catastrophically blows up on all the multilingual data. So if you manually filter for the right language and apply the FastX filter, that's the best possible thing. That's the second row. Our approach that we sort of propose, which is pretty simple, just estimate a bunch of correlations, is the second best thing in this plot over here. And if we look at kind of fine-grained per benchmark performance, we see sort of pretty consistent things here as well. So to help you read out this plot, each row is sort of a filtered data set. Each column is a task that we're targeting. And so if we don't do any filtering, this is the performance that we get. And the little boxes on the top left, this is the rank, just so that you know whether our performance is good or bad, right? So we want to be as close to 1, which is the red-ish colors, as possible. If we do language filtering, what we see this like diagonal structure, which is basically it does really well on the language that it's targeting. So for the English benchmarks on the left, it does really well in English, does catastrophically badly on everything else. And then for the multilingual data sets, it does well on its language and nothing else, right? This is what we expect out of language filtering. DSIR, which is supposed to be sort of optimizing for a benchmark, doesn't really even select for languages particularly well. When we look at our method at the very bottom here, the perplexity correlations, we kind of see for the English benchmarks, which is these columns over here, it does reasonably well on all the languages. When we filter for the multilingual data, when we filter for the multilingual data, we kind of see it does reasonably well on everything. When we filter for English, we see really bad performance on the non-English data set over here, which is kind of what we expect out of language filtering. So what this is showing is we get pretty same performance at a per benchmark level. We're matching sort of the best known heuristic data selector, which is the FastText classifier method. The other kind of interesting side note here, right? So we're using this all to construct data selection algorithms. But one thing that is generally true is that perplexity correlates very strongly with sort of model performance. Like I think we like to think that each benchmark is a really unique object. You can't really, predict the performance of models on a particular benchmark very easily. But if some weighted sum of log likelihoods on pre-training data correlates quite well with the actual rank of these 90 different models on data sets like PI2A or French Lambda, which I think is a kind of interesting observation that might be useful more generally. And then finally, the core primitive that we're using here is essentially this big matrix where we have on the rows sort of different domains, and on the columns we have these different models, and each entry is a log likelihood. And if we look inside this matrix, we actually see pretty clear structures in the data. So this is a TSNE plot of essentially this big matrix. And what we see is like really clear clusters for language on the left side. So they're very well separated in this matrix. And on the right side, the other thing that we see, which is a really continuous structure that's embedded in here, is the average entropy of the different domains. And so there's a lot of rich sort of data-related structures embedded into this big loss matrix that we're actually operating over. And so it might be a useful primitive more broadly in data work. The last thing I want to talk about is not actually directly in the line of sort of what is the technical way we're solving this problem. It's much more about how do we, validate our results and how do we make sure we don't sort of fool ourselves that this method actually works. And so some students and I have been sort of trying a new way of thinking about sort of pre-registration based validation of some of these kinds of experiments and claims, right? So many past results haven't held up. I have experiments with 160 million parameters. There's an N of 1 in the choice of which pre-training data set we use and the various benchmarks that we picked, right? All of this, should rightfully make you suspicious of the external validity of the results that I'm talking about here. So what we're trying is essentially also to pre-register a bunch of scaling experiments to scale up about 100 times in compute, pick a standardized setting, which is DCLM, that we haven't ever touched or analyzed before, and use the same or pre-registered hyperparameters and report these results regardless of outcomes. And I think this, creates a new nice dynamic in terms of maybe helping us report negative results or sort of being much more clear about the scope of when these kinds of results actually hold. So I'm excited more broadly about these kind of pre-registration based approaches to doing better science, especially if we're doing scaling work. Okay, to sort of put this section together, it's quite clear that data selection for pre-training is a place of enormous leverage, right? All of the companies building these language models have dedicated tons of resources into thinking about data selection. Algorithmically, though, we have made very little progress. And so here I've presented kind of two ideas in some sense that let us make hopefully progress. One of them being leveraging the large number of models that are already out there, right? This observational approach to building these kinds of predictors. And the second one is to reduce it to simple high-dimensional regression problems and using off-the-shelf tools in some sense to solve them, right? So we report some positive results. As I said, I'm more excited about sort of the pre-registration and what the follow-ups will reveal. But we've seen some important ingredients, like looking at the losses, building high-dimensional single-index model estimates, and then small-scale validation. If anyone has questions on this part, I'm happy to answer them before I move on to the second part, which has a pretty different flavor. Yes.
So I think what we're doing here is that you're trying to find those domains where the language modeling performance correlates well with performance of the benchmark.
Yes.
But it could be that the causal direction is actually reversed, that if your model performs better on the benchmarks, they are actually already fitting very well the data set that they have low capacity in.
That's right.
I also feel that if that's the case, there can almost be a counter argument that you almost want to select those data that you have high complexity in, because training on them have the best chances of marginal improvements over the data. So
that's right. Yeah, I think maybe the most likely true causal model is actually there's these latent variables which we do not observe that are the actual things that people intervene on. Like for example, you would intervene on, say, using Wikipedia or not, right? And that shared common confounder affects both the benchmark scores and the log losses. And the hope here is that level of joint confounding is sort of a lesser order factor, or at least the correlations reveal enough for us to be able to pull out what we want. I think one thing that really helps us is the last fast text step that we do, because then we're not actually selecting individual domains anymore. We're actually sort of smoothing it out into some sort of predictor that hopefully, because of its content-based nature, can't really rely truly on the sort of indicator of the confounding variable. Cool. Okay. So now I'll talk about a second part, which is essentially trying to think about parametric knowledge stored within language models and whether we can sort of put this kind of new niche knowledge into a language model. And so this is joint work with Zitong, who's a new stats student, Neil, who's third year, and then collaborators from the stats department, Shuangping and Emmanuel. So going back to a bunch of slides now to our motivating questions, right? We know that LMs struggle beyond the head of the distribution. We would like them to have, knowledge in whatever domain we're deploying them in. Unfortunately, if those domains are, populated with rare entities, our LM is not going to do very well. And so this is not, by itself a problem. There are ways to make language models better on targeted domains of your choice. There's been many papers doing so, mostly in things like medicine and math and law, there have been very nice papers deploying continued pre-training to make models have better, parametric knowledge and ability to handle, math and law and so on. I think the big issue is if you look at the rightmost column here, all of these methods are incredibly data hungry. You need roughly like 15 billion high quality tokens to get a language model to do, measurably better on a particular domain. And that's a kind of bad place to be because, most of the kinds of like niche domains that you have, maybe you have a single book describing a particularly important concept, or maybe you have internal documents totaling a few million tokens. Those are not settings that we can really handle using continued pre-training. And so the setting that we're going to consider is we're going to take a collection of about 100 or 200 articles and books, and that's going to total 1.3 million raw tokens. This, as we'll show experimentally later, is completely out of reach for any continued pre-training. Like you run a continued pre-training algorithm on 1.3 million tokens, it will do worse than if you had done nothing at all. So now let's ask, like, what can we do in this very, very data poor setting? Like, is there anything that we can do? Right? And as I said before, I'm not going to attempt to innovate deeply on the underlying algorithmic approaches. I think one argument for why the state of things is so bad is because, auto-regressive training on, tokens is just not a very data efficient learning algorithm, right? And I think many have described the drawbacks of this. So one example of this is, let's say this is from the abstract, right? We propose to bridge this gap with synthetic continued pre-training, and then you continue it on with whatever's after, right? So, if I go in the auto-regressive direction, what does synthetic CPT do? Then that's a pretty easy task. I can continue it with the continuation. If I go in the reverse direction of saying, like, what method synthesizes a large corpus, this is a much harder task for language models because it was never trained on sort of this key value pair of going from one side to the other. And so, papers like the reversal curse and so on have talked about this kind of at length. And I think, this kind of sheds light into why continued pre-training doesn't work in low data domains. During pre-training, we take, a piece of knowledge and we present it in so many different formats, right? Like in Wikipedia as an article, in Stack Exchange as a QA, and so on and so forth. Whereas I think in all the continued pre-training works that I had seen before, it's very limited diversity. We're operating on the raw tokens, which is limited both in the format and the way the sort of content, sort of the inferences that you might draw from these books. And so as I sort of started earlier and motivated this talk with, we're not going to try to change the learning algorithm. Maybe that's the better long-term thing to do, but for now, let's try to do something that works, right? And so this is maybe the simplest thing that you can do in this setting, which is to try to say, I'm going to bridge the gap between continued pre-training data and pre-training data. And how am I going to do that? Well, I'm just going to try to replicate the underlying diversity that we see during pre-training. I want to vary the kinds of topics or the kinds of entities that I'm talking about in my documents. I want to vary the style of how it's presented. And in general, I want to make sure that the data that I have to do continued pre-training on is diverse enough for us to really make progress, right? And this is very different in motivation to, I think, a lot of what the synthetic data community has been thinking about in general. I think there's been a really interesting line of work thinking about compute and model size efficiency. Like the Microsoft people with Phi have been really pushing at this very hard. The open source community have been thinking quite a bit about how do we build better instruction tuning data using language models as data synthesizers or for very specific narrow domain tasks. We're not thinking about either of those questions. We're thinking about the question of, can we, in some sense, turn a limited domain into something that looks a lot more like pre-training data and reap the benefits of pre-training? So, okay. The thing that I think is also important is, okay, so now I've laid out the broad vision and setting for where we want to be. Now what we need is sort of the concrete execution and measurement device by which we measure progress, right? So reading comprehension for long context models is actually already the perfect setting by which we can evaluate data efficient continued pre-training. So one example, the one we evaluate on in our paper, is quality books by NYU and Anthropic folks, where they take a mix of Project Gutenberg fiction stories, Slate magazine articles, and some nonfiction articles. These books are not that common. People don't talk about the knowledge in them very much. So the pre-trained models don't know this very well. And they come with very high quality QA evals. that are written by humans. And so each of these books has associated with them a bunch of multiple choice questions that we can ask about them, right? So there's about 1.3 million tokens here, so that's far too small for continued pre-training, and we can evaluate really nicely on this data set. Just to contextualize performance before we start, if you ask Llama 3.1 or GPT-4 questions from this data set, you'll get about 51 to 39% accuracy. So there's a ton of headroom in terms of how much we can improve this performance. Yes?
Just to confirm, the headroom's really there. If you give them RAG, then they do great.
Yes. The RAG performance of GPT-4 with an Oracle RAG that has the answer is like 90%. I think I'll have the numbers later. It's very, very high. Yes, that's right. Yep. And there's a human level baseline in the original quality paper, which is close to 100 as well. So for many reasons, I think this is a quite a tractable task. Okay. So attempt number 1 is just do continued pre-training, right? I have 1.3 million tokens, but if I tune my hyperparameters hard enough, maybe I can get that to work. We try the simple thing first. Doesn't work at all. So the dashed black line is where we're starting. That's Llama 3 base. So all the experiments here are going to be on base models, because I don't want to try to replicate the instruction tuning right now. The green line is what happens if we do continued pre-training with any amount of sort of non-trivial amount of continued pre-training tokens. No matter how we tune the hyperparameters, just training at all on this raw token just makes the model worse. Okay, so attempt number 2, and this does kind of work, but very slowly, is to cleverly rephrase the data. So let's just do some paraphrasing and take the documents that we have and rephrase them in various ways. In particular, we're using probably the strongest baseline that we can here, which is the prompts from the Rephrase the Web paper from some Apple folks earlier this year. And so, performance gets better and we exceed GPT 3.5 level performance with about 20 million tokens, but scaling is relatively slow. I do note, however, that this does seem to scale nicely and predictably once we fix a few things. Yes?
The paraphrasing model that you use is the same base model that you use in experiments?
That we use in the experiment. We use GPT 4.0. So this one is using a stronger model to paraphrase for a smaller model. But we will eventually exceed GPT-4 performance. So it can't really be explained by distillation effects, just to be clear. So I think there's a broad thing that I think is an interesting sort of thing about synthetic data, which is LLMs in general are not terribly diverse. If I ask a LLM, paraphrase for me random samples, and I sample from that, sometimes it works well, but oftentimes the diversity that you get is very limited. So we see that in this left plot. On the right is a plot from a recent other paper with Chenglei Si and Di Yang on research ideation, and we found if we ask a LM to brainstorm new research ideas, there's a few new ones, and then rapidly as you generate more and more ideas, you're just repeating the old ones over and over again. And so increasingly common is using some sort of external source of randomness to enable us to get more diversity. And so, maybe you're conditioning on random human seed data, or conditioning on past data you generated, or conditioning on different combinatorial sets of like skills that you've enumerated. And so what are we going to do? We're going to do something very similar to this idea, which is, we're going to construct something that looks like a knowledge graph, a bunch of entities. And then we're going to randomly choose pairs or singletons of these entities. And then we're going to try to sort of trace the path between them in the knowledge graph. The choice of these entities is going to be a source of external randomness that induces diversity. And so the actual algorithm that we do is the following. We are going to first prompt the language model for entities in a knowledge graph, or just entities in a source document. So imagine I have a source document talking about Da Vinci and Mona Lisa and Louvre and Lily and James and all these entities. First, I get the list of the vertices in this graph. I'm then going to sample random k subgraphs of the knowledge graph. So I'll say I'll sample Da Vinci and Louvre. And then I will have the data generator LM synthesize descriptions of entities in this subgraph, right? So I'm going to have GPT-4, let's say, describe what is the relation between the Louvre and Da Vinci. And it will generate, essentially the path, roughly speaking, corresponding to this, right? And so now, you can think of this as trying to, construct new deductive closures. The original document, of course, contains a bunch of explicit facts. There's also implied facts in the document that are not explicitly mentioned. And so by doing this, we're picking random pairs, and we're forcing GPT-4, with its in-context conditioning and sort of generation abilities to generate explicit text corresponding to implied facts in the original document, right? And we're not really synthesizing information from thin air. This is information that existed in the document. What we are really doing is exploiting the gap between the data efficiency of in-context learning, which we know is relatively good, and the data efficiency of gradient-based pre-training, which is truly terrible, right? So we're trying to just bridge that gap and use one side which we know is good to try to bootstrap the other side. Okay, so where does that leave us? Okay, so if we do this sort of knowledge graph centric augmentation strategy, we get fairly rapid scaling that continues on and on past sort of GPT-4 as we sort of scale our data collection strategy. We terminated rephrase CPT after about 20 million tokens, since it was pretty clear that this gap wasn't going to be closing with just more tokens, right? So we get predictable scaling gains, much like pre-training and so on, without having text in front of the model like you would in a RAG system, right? Now we get 55+%. Okay. Jason asked sort of, or not, this is not Jason's question, that one will come later. So, I want to just put those numbers into perspective, right? If we do continued pre-training, the left top number is sort of the very top of that graph, 56%. And our teacher, which was GPT-4, even in the best case is 51%. So even if all we're doing is distillation, you can't really explain that last 5% gap that we get. And this is really not surprising, right? GPT-4 just doesn't have that much knowledge of sort of the niche books that we have. Most of what we're getting out of GPT-4 is sort of this like rephrasing thing that we have, right? And the gains from the base model are really significant. That's about 17%. Of course, this is kind of cool, right? We have nice predictable scaling on QA. But in a way, I think if you're skeptical, I think you should be saying, well, fine-tuning a model for QA is not hard, right? We knew how to do that with BERT, or T5. So now I think the thing that is interesting and shows some potential is that you can get the same kinds of like multitask generalization that you would have in a normal language model. So we instruction tuned this model that we built with Antigraph. And then we just started asking it various other kinds of tasks that we can do. So this is a qualitative example. I've asked for summarization. I've asked for like a bullet pointed list. I've asked for compare and contrast some authors to articles that are in the corpus. And it sort of does a reasonable job at all of these things. So we start to see a lot of this like instruction tuning ability where it's leveraging this continued pre-trained knowledge, which is very encouraging if what you want to do is build a multitask model. In the summarization case, we see really clearly that continued pre-training helps a lot, right? So once again, if you ask it for a summary using a short summary prompt, for a particular book called Cosmic Yo-Yo, the continued pre-trained model at the very top, mostly free of hallucinations. We're not giving it the article at test time. And so from parametric knowledge, it's able to give this nice summary. If we give it the sort of the raw continued pre-training model, so this is continued pre-trained, but without rephrasing or anything else, we see sort of a bunch of hallucinations. We see the same thing with kind of the rephrase model. Over here, we see a bunch of hallucinations highlighted in red here. So we see significant improvements through Antigraph. And then, we can make this quantitative, right? We can evaluate what's the rate of hallucinations, like the false claims, what's the rate at which we have salient claims. And we see quite clearly sort of, a short prompt where we're saying summarize with a short summary, and a long prompt, give me a very long summary. In both of these cases, we have very low rates of hallucination and a fair number of salient claims. Of course, humans are much, much better than, closed book summaries of books that we can get in Antigraph. But still, we see significant improvements relative to the original starting point or sort of raw CPT or even GPT-4. And so once again, this is showing that this is not pure distillation effects that we're getting here. The same is true. I was showing you sort of the rephrase model was pretty good. The same sort of comparison holds as the QA case. Antigraph, which is the yellow here, if we subsample that model to be token matched with rephrase, we see fewer false claims. That's the y-axis moving downwards for the yellow points relative to the blue points. Although notably, I think the gap is smaller here than in the QA case. Okay, the final thing I wanted to talk about was sort of retrieval augmentation, right? Clearly, you would not just try to pack all of the knowledge of the world into a language model. That seems crazy. You would actually put the documents in front of the model and have it answer questions, right? You would use a RAG system. But the point here is that having a more parametric knowledge in your language model would be helpful for RAG as well, right? You know how to manipulate the knowledge in your domain much better. And so what we see is if we look at a RAG system, so the Ngraph CPT plus RAG on the left, and sort of the non-CPT model RAG system in the middle, we see 2.4% or so improvement in the RAG system when we take the CPT model and apply it with RAG. And I think one thing I want to note here is that we wanted kind of the strongest possible baseline here. So the RAG system uses stuff like metadata, and the queries always have the metadata. So our recall rate of getting the right article is almost 100% in all the cases. It's like 99.5%. So this is like a very, very high performance RAG system. We still get about 3% gains. And once again, this was Jason's question. What's the headroom? 86 is the sort of top level accuracy of GPT-4 with this RAG system. Okay, I only have a few minutes, so I'll just sort of give the high level intuition here. So I think one thing I want to make clear in all of this talk is, this synthetic data stuff isn't magic, and we're not trying to synthesize knowledge from thin air, right? Like that's a sort of impossible dream in a sense. All we're doing here is much closer to classic perspectives and say data augmentation or sort of query expansion and these kinds of things, right? We're rewriting the same piece of text in many different ways. And so, can we build a deeper understanding of this rewriting process? We built a toy mathematical model where, let's say we have a set of entities that appear in a single document, so that's V, and claims that directly appear is, edges in this knowledge graph. And so what Entity-graph, this process, is doing is it's sort of connecting different, connected components, right? In the limit, as we continue all of our augmentation, we're going to be able to densely connect all of the entities within each connected component of this knowledge graph. We can't hope to do more for any two disconnected components. We know nothing about their relations. We can't possibly fill that in, right? And so we built a formal model and we analyzed sort of what happens on this like sort of random graph model. And sort of the punchline here is that we can sort of show that the asymptotic behavior of this is going to behave exactly like the connected components of this random graph. So it'll have this like mixture of exponentials, scaling curve, and then it will have a very clear asymptote. So you can't get to 100%. That's really the main takeaway that I want to give with this sort of theory potion. I don't want to go too deep into that component here. So, okay, at a high level, I think my takeaway here is it's going to be, as compute becomes more and more abundant, it doesn't feel that way because we're academics, right? Like we're very, very compute constrained in everything we do. But the GPUs get faster every year, and the amount of data available is going to stay constant. And so for everyone, OpenAI and us and everybody else, handling tail knowledge and data efficiency becomes increasingly important. And we don't need necessarily new algorithmic interventions to even sort of bridge that gap, right? Like we can get to pre-training style learning being data efficient by doing things like data augmentation using LLMs. And the last thing I want to highlight is the sort of last bullet point. I think continued pre-training on these kinds of reading comprehension data sets is actually a pretty exciting test bed for data efficient pre-training, because you have this very small document or very small amount of knowledge with sort of this nice high quality QA evaluation. So it doesn't take a ton of compute to evaluate, and you can build algorithms and test things in this test bed. And that's kind of why we were working on things like quality. Okay, and to combine all of this, right, it's quite clear, or people have been saying for a long time, data is really, really important. The same holds true for pre-training and language models and so on. And so thinking about more algorithmic control, both of the pre-training data selection and over synthetic data generation, seems like a really interesting sort of meaty direction for us to try to make progress on. Thanks. I'm happy to answer any questions.
Let's do two questions. So, I guess maybe it's a dumb question, but they seem like conflicting things. One case you're getting rid of all the data, the other case you're generating much data.
Yes.
How much of your synthetic data would you get rid of if you applied your data selection strategy?
Oh, interesting. Okay, I didn't think about it that way, but I actually think so these two, I think, do live in different paradigms. Like the first one is in the compute limited regime where you can't train on everything. And the second one is like the data limited regime. But I actually think they kind of come together in an actually more general thing, which is data transformations, right? You can transform a piece of data by like sending it to the void. You can transform it by augmenting it. But actually, one interesting thing that I haven't studied and I am thinking about now is, let's say you have a bunch of very low quality data. Like, can a rewriting of that really help you? And you can rewrite it in many ways or a single way, but that seems like the more general principle here. And so I am very interested in that general thing. And building like data valuation mechanisms to support it, I don't think this data valuation thing is robust enough for that level of optimization. But I think that would be the key. Yes.
If you tried this like anti-graph approach with other domains, and specifically thinking that even if these models haven't seen these particular books and articles before, these models have seen lots of books and articles. And so the quality of your synthetic data in a totally new domain that's really different is going to be worse, potentially. And similarly, your entity graphs are entity graphs are something that make a lot of sense for books and maybe less sense for domains that have less kind of connections between people.
Yes. Yeah, I think that's a great point. Honestly, I think entity and knowledge graphs and QA-centric, like in some ways, this is a very QA-centric approach, is, I think, limited. Like, I think a stress test that we were thinking of that we can't handle with any of this is like, could this work for tabular data? Like, if you found a JSON somewhere on the internet, could you use this to generate useful English data? I don't think we can. I think this falls, once again, in the kind of data transformation space. Like, if we could think more than like augmentations, more about transforming data, then we can maybe start to think much more like seriously about like, you get a pile of JSONs, give me a thing I can pre-train on that gives me knowledge to do QA. Maybe some of the classic semantic parsing data sets, like tabular QA stuff, would actually be really interesting for that class of things.
Well, so other people should go first.
Yeah, you have a naive question. When you, like a lot of these training might only go over one round. If someone wanted to do a series of continued pre-trainings, should you think about it as doing everything at once, or does going one by one eventually degrade other, like if you did one after the other, the previous models?
Yeah, so I think I don't have a conclusive answer to that. What we found in terms of sort of the forgetting style problems is with careful rewarming and careful replay. So you replay, in our case, we took red pajama V2 data and like shoved it back in during continued pre-training. If you were to do the same thing, but like shove in, for example, previous stage continued pre-training data back in as you follow on, I would guess that you can like retain a lot of the performance. I think the real question is, it's probably going to cost a lot of compute to do this as you're replaying more and more data. And the hyperparameter optimization costs are extremely high, I think. So I think there's major challenges there, but it might be doable. From at least what we've seen, we didn't see much degradation. Yeah.
I thought about building a similar predictor, but use it for pre-training. So you have a predictor, and then you can just this time pre-train on performance on benchmarks instead of like from last.
That's okay. I see. I think this is an interesting question, or at least my interpretation of your question is pretty interesting, which is, can we train on like benchmark-like data, almost like just transform everything into a benchmark and see how far we go? I'm pretty curious how far we can go if we just transform everything into a benchmark, basically do GLAN P5, but with synthetic data. I think some of the open source instruction tuning data sets get to this, like Ultra Chat, for example, is like multiple million conversations of transformed synthetic data. And it does do well, but it's not quite as good as pre-training, of course, right? Like you can't just brute force your way there. So I am very curious about the scaling properties. I don't know if I'm optimistic about that, like solving a lot of the problems.
Also, benchmark performance as a training loss.
Can you use benchmark performance as a training loss? I mean, unless you're doing supervised fine-tuning on benchmarks, you can't quite, right? Like you have to train on something, and the something is either pre-training documents and next token prediction, or I mean, you can train on benchmarks, but that's a different objective, right? Like we're basically building a surrogate. Like we want to sort of link the two, and that's kind of the thing that we're doing in the first part.